something in the website, course website, such that if something pops up, you can get notified. And so it's mostly like first come, first serve for the registration. But and because of the classroom is exactly 48 seats, so we would appreciate it if you're not registered for the course for credits. You can maybe come to the classroom a little bit later. So just to make sure like students who register for credits can have a seat. And we'll try to see like if there were, we can find some extra chairs from the hallway, so like additional students can sit. So in the worst case, like I mean, if you can maybe bring your own chairs in some manner, if you're like auditing the class, like you can definitely do so. And the other thing is the course is recorded, so if you're interested, you can like reach out to me, and I would try to add you to Canvas, so at least you can like look at the recording after the course. So yeah, the first two lectures are gonna be mostly about some basics of machine learning and like just overall concept and some, I think, the principles of machine learning, just to make sure that everyone here gets familiar with that. But I'm pretty sure like a lot of you have already this kind of lessons before, so feel free to adjust the pace as you like. And like, if at any pace any question pops up, feel free to raise your hand and ask the questions. All right? Cool. So let's get started. Yeah, so since our class is called Machine Learning for Bioinformatics, naturally the first question you will ask is like, what is machine learning? I think the concept is getting really, really broad right now, and it's covering a lot of different areas, which may or may not even involve learning. But I think there are pretty much a lot of definition given by the people in the past. For example, like learning is the process of converting experience into knowledge or expertise. And sometimes the people who are working with pattern recognition would say the goal is to develop methods that can detect patterns in the data, so they can use this and then use these uncovered patterns to predict future or predict the outcome of interest. And mathematically, there are also definition saying that you can define the learning task as given the value of an input x, and you want to make a prediction of the output y, denoted by y hat, which is a little bit narrow definition. So we will see that this definition may not hold anymore in nowadays modern machine learning. But I found this one definition pretty general. It's from Tom and Chill, who wrote the great book of machine learning textbook, where the definition is, I think, makes a lot of sense, where we just say machine learning is where we try to build a computer programming. Nowadays, usually like maybe a deep learning model or like a Python program. And it can learn from experience E, and the learning is done with respect to some class of tasks T, and you have some measurement for the how good you perform those tasks, and so measurement with some measurement P. So in general, like if its performance at tasks in T measured by P will improve with more experience you get. So the more experience or more data we have, we kind of expect the performance at these tasks measured by P would increase. And there were some notations. I think a lot of time these notations were kind of interchangeable sometimes. And you might see like a slightly different notation, but in general, the notation involves just like regular mathematical notations to represent whether a scalar or vector or matrix, which are the most commonly used in kind of linear algebra level courses and basic like linear machine learning tasks. Whereas in the geometric deep learning part, we will dealing with even higher dimensional data, which also involves some computation over tensors. And we're going to use the calligraphic letters to represent sets and space or domains. And we will be dealing with some superscripts or underscripts, which is just note like the cardinality of the sample or the index of the sample or dimensionality of a particular sample. If not specified otherwise, we usually refer to X as the input features or features, and Y as the label or the output. And then this hat thing usually refers to a predicted value. So in the supervised learning, it will be the predicted label or the value in the regression task. And in generative model, it can also be like the denoised prediction, for example, in a diffusion model. Yeah, so in general, like X and Y, you may see them in different types of forms, not just in machine learning, but also in general, like statistics or other domains. But so they all basically referring to a very similar thing, where we try to learn a function f, which maps from a input feature X, defined over some domain of X, and we want to learn this function to map it to Y. So we can call this pair of X and Y as a training example, and a set of X and Y pairs as our training data set, which is usually the cardinality of n, where n is the number of examples or the size of our data set. And the output Y has multiple form. It can be like a binary label, or some people call it a response, or in the regression task, it's like a continuous scalar value. It can also be a high dimensional. It can also be a very high dimensional thing, such, for example, in biophysics, we want to predict the force of each atom at each timestamp, so the prediction would be like really high dimensional, and also varying with time. And talking about the models, of course, this might be an example on the kind of linear-based classifier case, but in general, we in the parametric machine learning models, we use some parameters which we learn through the training process to define the function f, which maps from the prediction x to from feature x to prediction y. And some notations, some names of these parameters, sometimes you call it weights and biases, especially in the linear model, which is a basic module of a lot of the neural networks as well, where the weights are just a linear coefficients in front of x, and biases is the intercept or the constant that you add to the linear function. And there might be other coefficients and hyperparameters and parameters, which we'll see defined in different types of model. And there's also like different words that we hear to refer to model. So for example, sometimes you can call it a classifier, a predictor, or call it hypothesis. And there are different types of model where there's discriminative models where try to explicitly make predictions of y, and there's also generative models where we don't explicitly model or predict y, but in general you try to capture the distribution of x, which is also like hiddenly controlled by the distribution of y. Types of machine learning. So yeah, I think this is a really kind of a naive categorization, but there's certainly more that we can do than this. But I think it's basically the most commonly used types of tasks in machine learning. Basically classification, regression. We will see some of these a lot in our first few lectures about, for example, DNA regulatory, where we care about the type, like the type of functionality or the magnitude of functionality and signals. Whereas there's also unsupervised learning, which will also pop up in our different stage of our lectures, where sometimes we care about knowing the structure in the data, for example, using clustering or low dimensional reduction techniques. And on the other hand, we also maybe use unsupervised learning or self-supervised learning to just learn a good latent space or good representation space that have a very nice property. And in terms of the y, you can also define it, we can also expect different modality for y. Yeah, so when it's an empty set, of course, it's like mostly semi-supervised, self-supervised, or unsupervised learning. But in a regression task, it's usually defined over a continuous real number. And we can also extend dimensionality to like higher dimensions. And in binary classification, we mostly deal with binary values like 0 and 1. And in multi-class classification or categorical data, we can represent those as one-hot, either one-hot distributions or call it one-hot vectors. And we can also represent them as with ordinary numbers, which are discrete, but not just 0 and 1. And which it's actually proven to be quite useful in some of the recent generative models. And an objective function, here we use J, but you can also see like L or R in some cases. But in general, like J, what the objective function is involved is usually we're talking about optimization, where the optimization, where the objective function is what we try to optimize, not just in machine learning, but in general optimization problems. And for the parametric models, when we optimize this function, is usually with respect to the parameters theta. And there are like multiple constraints we can add to the objective function as well. And when we talk about these losses, there are actually a lot of different losses defined. The common ones, for example, classification, involves this like cross entropy and 0-1 losses. And for regression, we can also compare the error between your prediction and the true label. And particularly importantly in Bayesian inference or Bayesian models or generative models, there's also the metrics called k-out divergence, which kind of describe like the distance between two distributions. And there's also likelihood function, which is also used a lot in both like a generative model and the supervised learning models. So we'll go into details. I'll go over some details of each of one of them and some examples. So for 0-1 loss, it's really simple as more like an indicator function where whether something is predicted correct, we'll assign a loss of one, and then something predicted incorrect will be assigned a loss of 1 and 0 otherwise. You can see that this is maybe a good metric for like looking at whether something is correct or not, but the function is kind of highly non-continuous and could be ill-posed and not be a very good thing to optimize for. And alternatively, there's also like cross-entropy loss, where in this case, if it's a binary task, it's mostly defined by the sigma of p log p. So you can see it's basically multiplying the labels with the probability that you predict with the corresponding probability assigned to that label. And we can further extend these. This is one example, but I feel like everyone should probably know how to compute cross entropy. If you want me to go over this example, please raise your hand. Cool. So we'll skip this one. And we can further generalize these cross-entropy loss to higher dimensional predictions. For example, with K classes instead of binary classes, it's essentially the same thing. It's just that the probability is defined over higher dimension instead of just two values, 0 and 1. And a lot of time, if we make multi-class prediction, we will use this softmax function, which will guarantee that our prediction is a formal probability. Any questions so far? Cool. So in the regression task, similarly, we can define loss functions. And since here the prediction we're making is over the continuous space, and the goal of training is to get accurate prediction as closest as possible to the real labels. We can define distance, like different types of metric for distance defined over this real space, real number space. So one commonly used loss is the mean squared error, which measures the square of the difference of two predicted value. There is also mean absolute value, or mean MAE, which calculates the definite distance between two prediction and the true labels. So like I mean, you can basically define different types of loss, but the high-level principle is the loss is easy to optimize, and it should be tuned for the type of problem or distribution that you care about. For example, the mean square error will amplify the scale of the errors. So if you have like values that are very close to each other, and like you try to differentiate learning from like values that are very consistent within like small dynamic range, it is better if you use the mean squared error, because you can tell very delicate difference from different, slightly different errors in predictions, versus if you have like a lot of some outliers in your data sets, then this mean squared error loss will amplify that error a lot, which might skew your prediction or make your classifier overly focusing on those outliers. So in that case, using mean absolute error might be helpful. And people also come up with combination of different errors, different losses. But it would be, I think usually it would be the best if you can frame your loss function and under some formally definition of likelihood, such as we make sure that we're doing like maximized likelihood estimation. And if we have some regularization added to that, we can also make sure that the loss function is representing some posterior prediction, posterior probability. So everything will be more principled. And when something goes wrong, you know it's like not the problem with your loss function definition. So how we train these models, how we do the optimization? Well, so like in the best case, what we try to optimize is the expected risk or loss associated with our model, our hypothesis model H. So basically, ideally, we want to take this loss function and compute the expectation of this loss function with respect to all data in the distribution of x and y. And we try to find the minimizer that minimizes loss functions to find the optimal hypothesis H. However, this distribution, a lot of time is unknown, it's high dimensional, and we only have some examples from this distribution. And we cannot write, most of the time, we don't have the analytical form of this distribution. And the other thing is, if we look at all possible function space, it will be too big and ill-defined. So empirically, what we use in machine learning is called this empirical risk minimization, where first thing, instead of computing the exact expectation with respect to the data distribution, we use these empirical examples, which is the training data, and just do basically average over the training data, which represent, with the law of large numbers, the true expectation of this loss function. And the other thing is we usually confine our search space or hypothesis space to some family of hypotheses. For example, you can define, if you're using polynomial function to approximate it, then your hypothesis space is confined to that family. And it's usually what we also refer to as inductive bias of our model. So we can see that these empirical examples or the data is really shaping our loss function, where we're relying on these examples to be a real reflection of the underlying training distribution of the problem. So if you have some bias in your data set, right, you will have a expectation, you will have an approximation of this expected loss, which also be a biased version of the actual expected risk. So that can cause a lot of issues in our learning, and so that's why we need to really think carefully about how you collect the data and whether your data is really representing the right distribution of the underlying probability. On the other hand, we also want to find a good space of hypothesis or the model families, which I will talk a little bit in later, taking multiple considerations, such that we have the most efficient and generalizable predictors given the data set distribution size. So when we're doing this optimization, we're very popular and almost like what everyone uses is called this technique called gradient descent. I will explain later why maybe this is something that empirically works for a lot of this non-convex function in deep learning space, but it doesn't mean that you have to use gradient descent. Like if you know that your function the objective function you're learning has certain good properties, especially for like convex function, you can definitely have more like bespoke solvers for these problems. But in general, what this gradient descent does is, of course, this is considered, we're doing like a parametric model again. We will basically find a random solution in the space, and we can compute the gradients, which is well defined in most of the case with respect to the loss function for all of these parameters, and we just do an iteration where we add these gradients with multiplying by some step size to the parameter we found in the previous time step. And once we do this for multiple iterations, usually it will point you will move slowly towards some optimum. It might not be it might not guarantee to be the global optimum, because it's really hard to guarantee in a non-convex function space. But practically it's working okay. And especially in big data training, since our data set is too big, it's really hard to, and also statistically inefficient to compute this loss function over entire data sets. What we do is to randomly split our data set into these mini batches, such as we can do multiple iterations of optimizations using these mini batches of the training data, and effectively over time, this will converge to as if you're doing the gradient descent on the full data set. Okay, so train, test, validation. This is usually what's involved when you do, especially a supervised learning task, where you have a clear definition, where you have a data set and you have some clear definition of performance, as for example a metric, which we'll talk about later in the class. So we want to make sure that we have enough data for training to minimize this empirical loss function that we talked about previously. And we'll also want to make sure the model generalized to new data. So, but the new data should come from kind of similar distribution of your training data as like an in-distribution test. So a lot of the time people will do this train test validation split, where you just randomly split your model into different parts. The other thing people do is when you kind of have some hypothesis that how you want the model to generalize, you might split the data slightly differently to control the variables that you want the model to extrapolate on. For example, in our protein modeling tasks, people can cluster their protein structures, and then they try to train on part of these clusters and try to generalize on the sets of clusters that are completely held up during training, to really show that your model is not just memorizing the training set, but it's able to generalize to new clusters. So I think the principle here is to really make sure what we want to test and what you hope the model to extrapolate on, to make sure it's not memorizing. And what the validation set is used is often to kind of tune how much we train the model, because this kind of optimization landscapes and the problem of overfitting and underfitting, which we'll also talk about later. The principle is kind of, it's a little bit debatable nowadays. Maybe some people don't use validation set anymore, but the practice is to hold out a small sets where they kind of representing how well your model generalize. And when you mean why? Yeah, because for some tasks it's just there's no a clean metric to define generalization. I think especially in generative learning tasks, it's kind of hard to measure how good the model is in some sense, depending on whether you'll be able to compute a analytical form for likelihood, or if there's metrics that are easy to compute during training time. Sometimes these validation can take a very long time, and people just skip that. So what we can practically do is to keep multiple checkpoints and just pick the one that gives you the best performance you want, instead of using this to do early stopping, something like that. And also I will talk about another phenomenon later, which in general this one-time descent and this phenomenon of the loss going down and up is kind of a little bit specific to classic models, where in the over-parameterized neural networks, we usually observe the phenomenon called like double descent or triple descent. So you can observe the loss function dropping again when you train longer. So you can observe multiple curves of like going down and up. So like this early stopping capitulated here isn't necessarily be the best methods for deciding where to stop. But in general, this is showing the concept that like our model can have this overfitting issue, which will stop the model from generalizing to new data points.
Why do larger models exhibit double descent?
I think that's a fantastic question. I think it's still an open question. It's like a phenomenon that we observe, but hopefully there's kind of inherent. I feel like there might be some inherent inductive bias in over-parameterized neural network that can try to learn these relationship between data better. And there's also like Walter Tickett's paper, which says that even you don't train, like if you just randomly initialize some like over-parameter network, it is kind of able to already capture some relationship between the data. Cool. So so let's move to the measurement of performance. When we train a model, we usually need to know how good our models are. So that's related to the performance measurement P that we mentioned in the beginning of the course. So for different tasks, there are different types of metrics that we care about. For example, the confusion matrix is usually used when we're dealing with a classification task, where you basically can categorize the predictions into 4 classes, where basically depending on what you're predicting is it negative and positive, and whether your prediction is correct or not. So there will be the true positives, for example, which means that your prediction is positive and the true label is positive. And depending on, so given examples from these 4 classes, we can compute different metrics based on the combination and ratio of different types of predictions from these confusion matrix. And some of them, which are commonly used, are, for example, accuracy, which is defined overall prediction you make that is correct, versus precision, which means out of the things that you think are positive, how many of them are actually positive, and recall, which means out of like this is usually associated with a threshold, of course, like the threshold where you calling something is positive or negative. And there's also F1 scores that try to balance between the recall and precision, which is also used a lot by computer vision folks. So one analysis of a predictor performance, a classifier performance, is called IUROC, where we try to capture the relationship between the true positive rate, which is basically out of your positive predictions, how many of them are actually positive, versus the false positive rate, which is out of your negative examples, how many of them are falsely predicted as positive. So we can see that this curve will goes up on the true positive rate because you're basically predicting more example as positive and definitely covering like all of the positive eventually. But this is at the cost of losing the false positive rate because you're now making more false positive predictions. So you can see that this metric only depends on the distribution of the positive and negative predictions. Sorry, the distribution, well, how to say? It only depends on your predicted value distribution of the of the positive samples and the negative samples. It does not rely on the absolute number of examples. So in that sense, it is a good metric if you only care about the relative like ranking, like how well you position the good ones in front of the negative examples. And it's insensitive to data imbalance, which can be a nice thing if you have a highly imbalanced data set. Then you shouldn't be really relying on like metrics like precision recall, because those will be biased by tons of positive data. But the other thing we can look at, well, sometimes you do care about knowing like how your classifier perform under a particular task, particular data distribution, which can be in balance, right? So in this case, we also look at the precision recall curve, where basically it's mostly focusing on your positive predictions, which means when you vary your threshold, how much of them, how much of the positive ones that you have actually recalled in your prediction, and out of the predictions you make that are positive, how much of them are actually positive, right? So you can see that if you have like a lot of negative examples, and then negative examples all have the similar distribution, but at the same cutoff, if you have more negative example, naturally you will always get more proportion of negative examples with the same cutoff. So that's why this metric will be biased by these data imbalance, but it also tells you under the current data distribution what is actually the precision and recall you get. So I think we need to make a good assumption of basically how much we want to weigh in the current data distribution that we're evaluating on to decide which metrics we want. And a lot of the time, a good practice is to look at both of them and try to strike a balance and argue this based on what kind of task you're doing. Oh, any questions so far? Cool. So now let's talk about regression. Since regression is basically involving with predictions of values, one thing that people use a lot in besides mean squared error is Pearson correlation, which also is also related to the error that you're making. But basically, we can be looking at the predicted value and the real value and see and compute this correlation, this Pearson correlation factor. And we expect if you predict something pretty well, you should have like a perfect correlation of 1, like the first one example. But of course, if you're predicting something that's totally opposite, you're kind of also able to predict it well with a -1 correlation. You just need to flip a sign of your predictor and get a perfect prediction. So there's another scenario where we don't care too much about having exact value prediction. As long as the ranking is correct, we kind of know like how to tell the difference. In this case, we can also measure Spearman rank correlation, which will directly compute this correlation over the rank of your predictions versus the actual value of the predictions. So how do we know our prediction is actually good and significant? So this is related to maybe some statistics tests as well, right? So a lot of time people just tend to like show a value and say, yeah, this is a good value or a bad value. Like I get 0.98 correlation, that's fantastic. But actually it's not that simple because this correlation can be they can be changing by like how many number of observations you're making, and like by random chance you might get similar correlation with the same number of observations, right? So this is why kind of we want to use some statistical tests to actually show that this correlation you're observing is make it significant enough such that you're really differentiating from a null hypothesis where like you can just randomly predict things and get similar predictions. So one such statistics people can use is this student t-distribution, which is a generalized version of normal distribution where you can tune like how wide or fat tail this distribution can be by deciding the different degrees of freedoms. So suppose we have the n number of observations, we can, and we have these R, which is derived like Pearson R, and we can compute the test statistic t here following this algorithm, and then using this distribution, we'll be able to see like how significant our value is here. So a random question: do you think for this significant test, is higher value better or a lower value the better? So raise your hand if you think p-value. For p-value, the larger means it's more significant. Okay, so everyone's correct. Cool, you're good students on statistics. Yeah, and then sometimes, like I said, sometimes maybe you don't care about something is higher or is positive or negative. So we can have this two-tail test where we just want to tell that these two are different. It doesn't have to be in one direction or not. Another way of testing the significance is to use this binomial test, which basically like try to model the probability of something can be correctly classified by a new like random model and try to see the significance of your predictors. And it can also be approximated by a chi-square test. One thing that people kind of tend to ignore from some time is about multiple hypothesis correction. Since that if we're basically testing multiple hypotheses or predicting, for example, PD model to predict multiple TF transcription factor binding, right? We tend to kind of, if we're only relying on the probability of doing one test, it doesn't factor in the fact that you're actually running multiple tests and you're getting a higher chance that basically the new model hitting a good correlation is also higher. So sometimes we want to make these multiple hypothesis correction to our statistics. One such way is just to basically multiplying our p-value with the number of statistics. And the other thing is called false discovery rate, or FDR, which you can basically decide a false discovery rate, and you rank the p-values that you get from your different tests of hypothesis and get a threshold where you can really call this is something that is significant, and then just only reject those null hypotheses. Another thing we want to emphasize is machine learning model can predict things that are correlating with the label well, but it doesn't have to be causal, right? So I think a lot of people use this example where you can see there's this very strong correlation between number of people who died by becoming tangled in their bed sheets and the total revenue generated by skiing facilities. So it's kind of totally irrelevant event happen to have like a high correlation. So it's really hard to argue that at the moment, and there's a whole field of like causal inference, which try to make these things more formal. But I think in machine learning model, like one easy mode that we try to fall into is to argue too much about causality when we observe correlation. So it's also something that we kind of want to think about, especially when we do these model interpretability. We use the model interpretability tools to explain our models. And the other thing is that the correlation isn't like really like a unique definition of. So basically, you can get similar range of statistics and correlation with totally different patterns of correlating with each other, right? So all of these plots here has the same correlation, or even same like mean and standard deviation, but you can see that they look very different. Your data distribution and your model distribution can entangle in a very different way. Okay, so that says. Now let's move to, so now we kind of know about how we measure our models. Let's move to talk more about the model itself, right? So let's say these tasks of, so assuming we have like two different features, the religiousness and the wealth, and we try to classify people based on these two features, like how well we can do in this task, and what kind of model do you imagine can be doing better than the other types of models, right? So it's hypothetically, because we observe some data there already, we can use the existing data to define a split of the space where things that are kind of similar to what you observed would tend to have a similar label. So this kind of ideology is I think in general, like a very general principle in machine learning, regardless of what kind of model you're learning, you can always interpret it as kind of some sort of metric or similarity in some space where you try to, the more similar you are to some of these training data, the higher probability that you can fall under that distribution. So one such model that like perfectly reflecting these principles is k nearest neighbor, where essentially for any given point, you just look at your k nearest neighbor and look at what the label they have. And depending on their label, you assign the prediction to the current data. So we can see if you use different number of neighbors, we can see that the space being divided like from a very fine grain make sure, so you can observe this really fine-grained separation of your positive and negative ones when we use k equal to 1, versus if you gradually increase the neighbor, you can get a more smooth, like, borderline or a decision boundary between the positive and negatives, and eventually you will be factoring in the more information about the the landscape of your neighborhood. And as we increase this number, you can get a smoother and smoother prediction of the probability of being being particular type of group. So like this k-nearest neighbor algorithm essentially directly built out of these principles of like following like how similar you are from your data. And you can see that in this across these different k is kind of the only parameter that you're tuning here to change the model, and it doesn't really rely on any model parameters, which defines a function of x and theta to map to such prediction. So this is what we usually call a non-parametric model, where like oftentimes when you make predictions, you're only relying on the data directly, your training data set directly, and compute prediction from your training data set, versus for the parameterized model, you will actually learn a theta from your data such that during prediction, you don't need your training data anymore, and you can directly make predictions. So there are a few things we can define to measure a model in a more kind of mathematical way. So two things we really care about in the model. One is capacity, the other is generalizability. So capacity is basically a measurement of how powerful your model is, which can be used to approximate different functions. So there's one very popular definition of capacity called VC dimension, which basically it describes like how many data points can you correctly predict with this model, given the worst case assignment of labels. Basically, imagine there's an adversary, you have like adversary that's trying to assign labels to your training data, and they try to make the problem as hard as possible. And in the hardest case, how many points you can still use the model? Like what is the size of data for which your model can still make a correct prediction, regardless of how hard the assignment is. On the other hand, generalizability is something different than capacity. Like people sometimes link the two together, but if you think about it, like capacity doesn't always mean generalizability, because generalizability is what we care about when we try to make predictions over new data points, versus capacity is only defined like over a set of data points. So, I mean, I think you might get this difference maybe if you deal with different problems for longer term, but the point I'm trying to make is like both of them are very important, and we really want to strike the balance, and we know what we care about is actually generalizability. So for simple case, like a linear classification, right? If we have like two-dimensional space, you can see that if we have a straight line, which is a linear classifier, you can only make correct prediction for all possible assignment of label for 3 points, right? When you add one more points to the label and you give these assignments to the model, then you're doomed. You won't be able to classify that with a linear classifier. So that says for this two-dimensional data, the VC dimension of this general linear classifier is how many? Who want to give it a try? Great, fantastic. Yeah, so the VC dimension for a two-dimensional space and this general class of linear classifier is 3. And in fact, if you look at the simplified version of linear classifier, where basically you always start from your origin and you can only add this scaling factor to in front of your feature, so you're kind of restricting yourself to only starting from the origin, then you will have even lower VC dimension of 2, because you won't be able to separate, for example, like if your origin is, let me think of yeah, like if your origin is here, like you can't split these 3-point tests very well, right? So then the VC dimension will be reduced to 2. But when we talk about linear classifier, we usually talk about this kind of affine version where you kind of you add this additional translation to the classifier, which enables you to kind of adjust slightly to like basically move parallelly on the y-axis, such that you will be able to classify 1 more points. And therefore, the VC dimension of a linear classifier for dimension of d is d plus 1. And of course, so as I talk about, there is like non-parametric class models like k-nearest neighbors, which really rely on the data, but it's actually pretty strong in terms of making these classifications. But the downside is that first of all, it's not really scalable, because the more data you have, you need to take consideration of all of the data. So that means it's kind of not scalable once your data set is huge. And alternatively, if you have a trained model with parameters, you will only rely on those parameters for making predictions. So your inference cost is a fixed size. But it can come with the downside that sometimes if you misspecify your model, you will have like a mismatch either in the hypothesis space, or your model is too low capacity, you won't be able to fit as well. But I think one key concept is that we usually found that k-nearest neighbor is pretty strong. So it's definitely a baseline that we always try to compare against in a lot of these regression or classification tasks. So we talk about this linear classification, but the class, as I mentioned earlier, it's more about deep learning. So how do we get more capacities with the same number of parameters? Well, neural network is one such cool model that kind of have proven to be a really approximate function approximator if you get unlimited width or depth. So the next part of our class will be moving forward to talk a little bit about neural networks. And in the later lectures, we'll definitely talk about more advanced architectures than the one that we're going to talk about today. So in general, so this is a very simple, actually the first version, the origin of neural network is called perceptron, where basically when we think about a linear classifier, the low dimension, the low VC dimensionality could be because of the line needs to be straight, right? So what we also call like linearity. So if we're able to curve our hyperplane line a little bit, we should be able to be more flexible, right, in dealing with these classification tasks. So adding the nonlinearity into these linear models kind of give birth to a whole series of more high capacity models, out of which neural network is one of such example, where in this perceptron case, the inputs is, so you can see the first part of perceptron is still kind of have this linear component. And what it does more is to add this nonlinear activation function, which really change things. And you were able to kind of curve your prediction and will also make it non-continuous in the output space, such that you can basically capitulate more complex landscape. And there's actually more than, there's actually a lot of different activation functions. For example, softmax and sigmoids are kind of the most commonly used, like as just when you try to build a kind of basic classifier that does not rely on stacking multiple layers. There's also like ReLU, which is kind of like a gated function where if things below 0 would have basically no signal, whereas when it becomes above 0, it starts to increase linearly. And there are also like some issues that we can observe with different types of activation functions. So a lot of these newer activation functions, they try to like, basically they're invented such that first they keep the same capacity of being nonlinear and being able to be the basis approximators of complex function, and it also gives you gradients that will help the model to train better. For example, the leaky value, because one thing we observe is like if your model is initialized in a really weird space, nothing has like positive activations. In that sense, you have like super tiny gradients because it can't almost like a stop gradient. So this leaky value let the model to give us a tiny gradients, even if you're negative, which makes the optimization more smooth. And sometimes in practice, it can give you some good performance. And there's also 10H activation functions, which kind of also give you a nice gating performance, but have a different range. And sometimes it's also like used a lot in these complex neural networks. There's also kind of units that try to normalize itself and try to add additional components like scaling and normalizations, such as, for example, SILU and GLU. And basically, I think there's a tons of a whole like theory, whole area of like studying different type of activation functions. But in general, we found that like it's really dependent on the particular architecture we're using. I think as we go over the course, we will encounter very different activation functions in some of the models later. So a single layer neural networks is kind of defined in, you can define like a single more basic block of a neural network where one layer is kind of comprised by these multiple hidden units, or we call it hidden layers, where like each one of them is kind of one example of the perceptron unit, and we try to learn these weight functions and biases, which do the linear map from our high-dimensional input to a high-dimensional hidden space, and we can also do another and it goes through these nonlinear transformations, and then we also we use another map from this latent space or hidden space to the final prediction layer, which is usually like a softmax or sigmoid function. And one thing we can see that this hidden space a lot of time you could try to increase the dimensionality in this hidden space, where you kind of try to learn higher dimensional features from the inputs, which try to capture like different patterns of your inputs, and which makes this model really powerful in kind of switching to different modes in your input data and being able to capture more complex pattern than the linear model, where you have to share weights for all to capture all pattern. So deep learning, basically we need to go deeper and repeat things. So when we say deep learning, I mean I don't know there's an answer to to this question, like how deep is deep learning, but maybe we can make a vote after the class. But in my point of view, I think more than 2 layers is deep, because you have like enough. Basically, you have like enough number of nonlinearity that you go through before making the final predictions. And of course, there's also like theories that we can use to kind of analyze the capacity of the neural networks. But in general, I think it's still like an open area where there are a lot of unknowns regarding the generalizability of a given model and the capacity of the model, because a lot of the theory relying on some assumptions of model either being infinitely wide or infinitely deep, so which kind of make the theory intuitive, but not super useful in some sense. But we can kind of treat that as kind of a intuition or guidance when we're trying to design these models. So how are we training the model? Well, it's trained exactly the same way as we defined in these simple models, which is doing stochastic gradient descent, where basically we can consider this entire model being the f function, which maps the x to y. And what we need is to compute the gradients of each of these intermediate weights with respect to our loss, which is defined over y, right? So this is kind of a computation graph of one layer, single layer neural networks. And you can see that like if we directly look at this function, it's quite complicated, especially when this like layer goes, the number of layers goes up. And how can we manage to do this? Well, actually, because of the chain rule, it's actually managed quite easily in for neural network training, where basically we can consider each layer in these neural networks being like one step of gradient computation, where we can factorize our gradients with chain rule, such that things that are closer to the loss function, we can compute the gradient first, and then we can multiply that gradients with the gradients in the second layer, where we only need to compute the gradients between the variables in the input and output of the next layer. So when we do this backpropagation, which we can basically effectively compute all of the gradients by flowing from the loss function and compute these partial gradients one by one, and then just multiplying them together. So it's a simple example of the classifier function we talked about earlier, right? You can see that if our loss function is the y times log of y, where for some of these y, it's if the class is C, then only the y of C will be 1, and everywhere else it will be 0. So you can see that in these loss functions, only when your label is 1, you will have a non-zero coefficient in front of this loss function, such that when you compute your gradient, only the ones that has a label of 1 here gets realized. And so sorry. So now that we know that for where only the C being the correct class, the loss will be realized, we can compute for. Then we can go further one layer down to compute the gradients with respect to Z for those nonlinear loss, and for those non-zero loss, in which if we just try to expand this softmax function, which is defined as the exponent of the largest predicting class of C divided by the sum of the exponent of all different largest predicted for the other class, we'll be able to derive the gradient for this Z for this hidden layer Z, which is computed in this way, right? So basically, the point is we can make one layer by one layer by propagation by computing this, and as you see that since these indicator functions and labels appears in every layers, effectively you will be effectively using the information of things that are predicted correctly to update our weights, where things that are incorrectly will move things in the opposite direction. And once these weights are computed, we would just use the normal gradient, the normal stochastic gradient descent, where we can set a learning rate to do this one-step update. So once we stack multiple layers on top of each other, it would just be the similar computation, and we can also make these gradient updates more complex depending on the optimization technique we care about, right? So now we get to the question of overfitting again. Like I think this also related to some of your questions earlier. So it's an interesting phenomenon. First of all, like when we try to specify the model, we try to strike the balance between what we call bias and variances. What this bias and variances mean is that with respect to different draws of your training data, because you only get one observation, one set of observation from the true distribution, right? But you try to model like a larger set of true underlying distribution, as I mentioned in the empirical risk minimization. You will get a model that can predict where the expectation of your model prediction has some bias with respect to the true prediction of a true value of that label. And this value can vary if you observe different draws of the data points. So essentially what this capacity or overfitting or bias versus variance we're talking about here is basically how your model change its behavior across different draws of training data. And in that case, if your model is super sensitive, is super high capacity, right? Imagine you're getting a very specific draw of your data, and you'll be memorizing that batch of data, and therefore you'll be getting lower, like much higher variance if you drawing different examples from the same distribution, versus if your model is kind of dumb, but it's kind of learning the. But if you learn your model is like lower capacity, you're probably getting a worse prediction because of this like low VC dimension and not being able to capitulate the right probability. But the variance you're observing with the different training data might be lower. So this can be derived mathematically, but I didn't put it here, so because it's not a theoretical machine learning class. But I think the principles is once we increase the capacity, you observe higher variance and lower bias. And what happens is that you're overfitting and you're memorizing your training data and generalize less. However, there's also these double descent or like triple descent phenomenon in our parameterized neural networks, where you could observe this second wave of descent, which can even go to like a better landscape. And this is actually shown, I think this is a really interesting paper that described this phenomenon. And they actually show that in the MNIST example, when you just increase the parameterization of your neural networks, you can really get this interesting double descent phenomenon. Okay, so when we think about capacity, right? It's really easy to tune your capacity by changing the number of parameters, for example. But is there other ways that we can regularize our network so it is kind of to guard against being overfitting? And in fact, there is also some other ways of doing it, which we call like regularizations, which basically means that instead of letting your model to freely flow in optimizing the ground truth loss functions, you try to change either the hypothesis space where your model can fall into, or you kind of change your objective that you're optimizing, basically injecting some noise into that. So one such technique, it's kind of broadly used earlier in deep learning, is called dropout, where basically during inference time, you kind of randomly choose some part of the network to activate. And you just train the subsets of the network, versus during the inference, you just kind of average out and just like directly multiplying that dropout coefficients to all the weights in your network. I think this is interesting, and it might has other implications. For example, like I don't know if we talk about like training like large language model, there's also kind of this, how to say, like a mixture of expert thing where you also kind of only activate a subset of neurons to capture some specific mode in your data point. So I think this regularization is, I mean, it definitely has some theoretical guarantee as well, but I mean, hypothetically, it's like really nice. The other thing we do is we'll call like batch normalization, which I feel like nowadays a lot of people just use batch norm instead of dropout, where you basically try to normalize your value in the batch such that it's always centered. And people also find effectively that could be kind of reducing a lot of the variance in the training. Of course, like why, I mean, as I mentioned, like overfitting versus underfitting is also a battle to strike a balance between bias and variance. So if you think of in terms of like variance that you're getting from the model, these kind of regularization really makes a lot of sense. Right, and the other type of regularization is explicitly enforcing certain prior or constraints to your function space, where some very commonly used regularizers are these L2, L1, or like maximum regularizer. They all some kind of try to normalize the norm of the parameters. So they are working sometimes in a similar fashion, but if you like look at their if we look at this graphical interpretation, the L1 norm is usually more sparse and kind of sharp, which is basically try to reduce the number of like non-zero parameters, where L2 is kind of just try to shrink the magnitude without necessarily like enforcing too much sparsity into them. So if we add this regularization to our neural networks, we'll be just getting kind of these additional parameters here when we do this loss propagation. And you can see that this is basically just tuning, like, basically trying to reduce the magnitude of your parameters or increase the magnitude of parameters by some level. Okay, so optimizations. Like I mentioned before, like optimization can be a non-trivial task for deep learning, which is kind of inherently because the function space we're dealing with is really complex, and it's not a convex function, it's called non-convex optimization. So briefly, like a function is called convex if, first of all, its domain is a convex set, and for like any 2 points, we can have this inequality here, basically kind of measuring like if the value is under if you draw a straight line between the two, like any interpolation in between is kind of under below this line here. And we know that for a convex function, of course, there's definitely a much better course to learn about this. We do have much efficient and strong guarantee for optimizer. However, like if you look at these are the convex functions examples. Actually, some of them look familiar, like exponent or like dislinear. Like some of them looks familiar in some of the neural network components, right? But sadly, if we compose these convex functions together, they're not necessarily convex anymore. And so that's basically why the deep learning models, which is a composition of like different functions, ended up being a highly non-convex function, and it can have like a really yield shape, kind of this really yield looking landscape. And this is kind of the two loss landscape from earlier the loss functions from the earlier generation of deep learning models on vision. You can see that there's definitely a lot of this local minimum, and you also have to go up to conquer a lot of barriers to get to the true optimum, which makes the optimization really hard, and a lot of the regularization or model innovations basically try to have the mindset to smooth out this landscape. So like given such a landscape, there are several things that we kind of observe. The first is like the steepest direction may not necessarily point towards the true optimum point, and therefore you don't want to go just briefly and blindly towards the steepest gradient descent direction. So you kind of want to balance the noise that you can get, where you try to like look at the different locations in your landscape and try to balance the gradients you get from different positions, and therefore you can use, for example, momentum methods or some other advanced algorithm. Just try to adjust your gradients with more global information than doing a single, than just going blindly with the local gradients. The one interesting observation also in the deep learning case is there might be a lot of local minimums, but there are also oftentimes a lot of equal local minimums that could be equally good to each other's, and therefore like reaching one of them is okay. Like, and there are also like a formal analysis of possible like exact same like equal local minimums you can get. Imagining like if you just do a different initialization of so one such simple example is like if you just swap the position of two hidden neurons, right? And then swap the weights completely, you should be getting exact same prediction, right? And these are two different models with identical prediction. So this is one example in neural networks that you can actually get multiple local minimum that are equivalent to each other. And there's also like a lot of literature that like really interesting literature that talks about these local minimum and how to like bind them together or try to do ensemble of them or just collapse multiple of them together. And yeah, I'm certainly not going to talk too deep about optimizer, but just to let you know that there's also this interesting domain that try to deal with optimizers. Well, in our case, I mean, as far as I have experienced so far, Atom is so strong. So effectively, like, we're just going to use Atom most of the time throughout our course. OK, and one interesting architecture that I really want to mention is these residual neural networks, which basically, intuition, the first intuition that it's introduced is to solve the vanishing gradient problem, where because of these highly nonlinear units in the network and stacking of those nonlinear units, you're kind of getting this vanishing gradient problem where you go, as you go down the to the bottom to the network, you get almost zero gradients a lot of time. So one such intuition inspired this like residual network where instead of going through all the nonlinear, you can choose to like skip them by directly having this X as an identity copy to the next layer. And there are a lot of different variation of such neural networks. Like you can make a combination of how many layers you skip and how you skip. And this is also like not recent, but like follow-up of that called DenseNet, where each layer has some direct interconnections to like all previous features. Basically, like how dense you want to add these skip connection to, and how you want to design such sparsity, the density of that connection. And it's ended up playing a really good job in smoothing out this landscape. As we can see, like the ResNet is kind of smoothed out the same training landscape by a lot, which makes the optimization really like easier and without like losing too much capacity, because it's supposed to be kind of, because the actual like model that you can get with this model is basically a subset of what we can get with the residual connection. OK, so I think that's pretty much the lecture today. So the next week, we're going to kind of talk a little bit more about deep learning training involving like hyperparameter search and architecture search. And also, we're going to talk more about the unsupervised learning regime. Any questions for this lecture? Cool. Then I think the class is over.